Pick up something near you and feel its weight. A mug, a phone, a smooth stone from a windowsill. That weight feels like the most ordinary thing in the world, a plain measure of how much stuff is packed inside. And almost none of it comes from the famous particle that people credit with giving the universe its mass. The Higgs boson, found at last in 2012, is real, and the Higgs field it ripples through is real, and together they explain why some particles weigh anything at all. Yet the mass you're holding is mostly something else. This is the mass problem, and we will build it up slowly, one plain step at a time. If you like quiet walks through real physics, take a moment to subscribe and stay with me. The question we start with is simple. Where does the weight in your hand actually come from? The stone in your palm has a weight, and that weight feels simple. It presses down. It asks a little effort from the muscles in your hand and your arm. Set it on a table and the table takes over the work, holding it up so you do not have to. We learn this before we can name it. A full cup is harder to lift than an empty one. A backpack loaded with books drags at your shoulders in a way an empty one never does. From the very start of a life, weight teaches us that some things have more of something than others. That's something we call mass. In plain talk, mass is how much stuff is in a thing. A brick has more than a feather. A planet has more than a brick. Pile up more matter, and you get more mass, and more mass means more weight when gravity pulls on it. This picture works well enough to build houses and bridges and to carry groceries up the stairs. For most of human history, it was the whole story, and it never failed anyone in daily life. But hold that stone a moment longer and a quiet question opens under it. What is the stuff exactly? Break the stone in half, then halve it again, and keep going in your imagination. You pass through grains, then specks too small to see, then molecules, then the atoms that make the molecules. Inside each atom sits a tiny dense centre, the nucleus, with a faint cloud of electrons around it. The nucleus holds particles called protons and neutrons, and those, we now know, are built from still smaller pieces called quarks, bound together by a force. So the weight in your hand reaches all the way down to the smallest things we know. The mass of the stone is the sum of the masses of everything inside it. That sounds like an answer, and for a long time people treated it as one. Add up the parts and you have the whole. The mass of the stone is just the mass of its atoms, and the mass of its atoms is just the mass of their particles, all the way down. Here is where the simple picture begins to bend. When physicists finally weighed the smallest pieces, the numbers did not add up the way anyone expected. The mass of a proton turned out to be far larger than the masses of the quarks inside it, added together. Not a little larger, enormously larger. The parts, on their own, account for only a small sliver of the whole. Most of the weight in your hand has no obvious owner among the particles. That gap is the heart of this story. We have a famous particle, the Higgs boson, that people speak of as the thing that gives mass to the universe. It is real, and it does give mass to certain particles. But the mass you are actually holding, the heft of the stone, comes mostly from somewhere else, and that somewhere is stranger than a particle. It is closer to bottled energy than to stuff. To see why, we have to go slowly. We will start with what mass even means, because there are two meanings hiding in that one word, and telling them apart is the first real step. Then we will follow the idea down through the centuries, from the people who first measured mass without explaining it, to the field that fills all of empty space, to the force that does most of the quiet heavy lifting. For now, keep the stone in mind and keep the question simple. You can feel the mass, you can measure it. What you cannot yet see is where it comes from. That is what we're going to build, one plain step at a time, beginning with a difference you already feel in your body but may never have named. Push a shopping cart that is empty and it rolls away easily. Load it with bags of sand and the same push barely moves it. Nothing about gravity changed in that moment. The cart is on level ground, and the floor holds all the weight either way. What changed is something else. A stubbornness. A refusal to start moving, and once moving, a refusal to stop. That stubbornness is the second meaning hidden inside the word mass. The first meaning is the one we already met. It is the heaviness you feel when you lift something against gravity. Physicists call that gravitational mass. It is the property that makes the Earth pull on the stone, and the stone pull, ever so faintly, back on the Earth. More gravitational mass, more pull, more weight on the scale. The second meaning has nothing to do with lifting. It is about pushing. Every object resists a change in its motion. A thing at rest wants to stay at rest. A thing in motion wants to keep going in a straight line at the same speed. The amount of that resistance is called inertial mass. The heavier the cart, the more it resists your push, even out in space where there is no weight at all. Inertial mass is why a truck is hard to get rolling and, just as important, hard to stop once it is. You can feel both kinds in a single object without ever weighing it. Take a heavy book and lift it, and you feel its gravitational mass pulling toward the floor. Now hold it at your side and swing it back and forth, and you feel something different. A drag at each turn, a resistance to changing its direction. That drag is its inertia. Same book, two faces of the same property, felt in two different ways. Here is the quiet strangeness that took centuries to notice. These two kinds of mass are not obviously the same thing. One is about how strongly gravity grips an object. The other is about how strongly the object resists being shoved. There is no plain reason they should match. Yet every experiment ever done says they do, to extraordinary precision. The mass that makes a stone heavy is exactly the mass that makes it hard to push. Galileo Galilei saw an early hint of this when he reasoned that heavy and light objects fall at the same rate. Because gravity pulls harder on the heavy one, but the heavy one also resists more, and the two effects cancel exactly. That perfect cancellation is not a small detail. It became, much later, the seed of Albert Einstein's theory of gravity, where the matching of the two masses is treated not as a coincidence, but as a deep truth about the nature of space and falling. For our story, though, the point is simpler. When we ask where mass comes from, we're really asking about this single number, the one that does both jobs at once, the gripping and the resisting. And that number is what particle physics tries to explain. When a physicist says an electron has a certain mass, they mean it resists being pushed by a certain amount, and it responds to gravity by the same amount. The question of where mass comes from is the question of why that number is what it is, particle by particle, and why some particles have a large one while others have almost none. So we now have a sharper target. Mass is not just heaviness, it is resistance to being pushed, a built-in reluctance to change how you move. Hold a thing still and you feel one face of it. Try to swing it and you feel the other. They are the same property wearing two coats. The next step is to follow the first person who pinned that property down with real numbers, who could measure it exactly, and who, for all his genius, never once claimed to know where it came from. Isaac Newton gave the world a way to put a number on that stubbornness. In the year 1687, in a book whose short name is the Principia, he laid out 3 laws of motion that still run through every bridge and rocket and spinning wheel. The second of those laws is the one that matters here. It says that the force you apply to an object equals its mass times how fast you change its speed. Push harder, and it speeds up faster. Make it more massive, and the same push speeds it up less. In that single line, mass became measurable. You no longer had to argue about how heavy a thing felt. You could push it with a known force, watch how quickly it picked up speed, and divide one by the other. The answer was the mass, a clean number, the same every time. Mass became the thing that links force to motion, the steady ratio between a shove and the response to it. Newton did something else just as powerful. He showed that the same mass governing motion on a table also governs the heavens. The moon falls toward the Earth in exactly the way an apple falls, only the moon is moving sideways fast enough to keep missing. His law of universal gravitation said that every mass pulls on every other mass, with a strength that grows with the masses and fades with the square of the distance between them. With it, he explained the orbits of the planets, the path of comets, and the slow swing of the tides. To make the numbers work, the masses had to be real, fixed properties of each object. Newton treated mass as a given. It was, in his words, the quantity of matter, measured by an object's density and its volume taken together. A thing had a mass the way it had a colour or a shape. You measured it, you used it, and the laws did the rest. They worked so well that for 200 years no one had any reason to ask the deeper question. And here is the quiet thing about Newton's number. It explained everything mass does and nothing about what mass is. His laws tell you, with breathtaking precision, how a massive object will move and how it will pull. They do not tell you why the object has the mass it has, or where that mass came from, or why one lump of matter carries more of it than another of the same size. Mass entered Newton's physics as a starting fact, not as something to be explained. This was not a failure on his part. It was the right move for the problem he was solving. To predict the orbit of Mars, you do not need to know why Mars is massive. You only need to know how massive it is, and then the laws carry you the rest of the way. Newton was honest about the limits of what he had done. Famously, about gravity itself, he declined to invent a guess as to its underlying cause, choosing instead to describe how it behaves and leave the why for later minds. So Newton handed down a perfect tool with a hole in the middle of it. Mass was the most reliable number in physics, woven through every calculation, and also the least understood. It was the quantity you always knew and never questioned. For 2 centuries that was enough. The machinery of the world ran on Newton's mass, and the deeper question sat untouched, waiting. It would take a new kind of physics to crack it open, one that did not treat mass as a fixed lump of matter at all, but as something that could flow, convert, and even appear from pure energy. That shift came at the start of the 20th century, from a patent clerk in Switzerland, in an equation so short that almost everyone has seen it, and so deep that we are still unpacking what it means. In the year 1905, Albert Einstein published a handful of papers that each reshaped physics, and tucked into one of them was a short relation that has since become the most famous in all of science. Written in words, it says that the energy of a thing equals its mass multiplied by the speed of light, and then by the speed of light again. The speed of light is a huge number, about 300 million meters every second, and multiplying by it twice makes the link between mass and energy enormous. What that relation says, underneath the fame, is that mass and energy are not 2 separate things. They are 2 forms of one thing, like ice and water, able to turn into each other under the right conditions. A small amount of mass holds a vast amount of energy locked inside it, because of that doubled multiplication by an enormous speed. This is why the sun can pour out light for billions of years from the slow conversion of a tiny fraction of its mass, and why a nuclear reaction releases so much from so little. For our question, the relation cuts the other way too, and that direction is the one that matters most. If mass can become energy, then energy can become mass. Energy that is bottled up, held in place, trapped and unable to escape, weighs something. It adds to the mass of whatever holds it. This is not a figure of speech. A stretched spring weighs a hair more than a relaxed one, because the energy you stored in it counts as mass. A hot object weighs a touch more than the same object cold, because the extra heat energy has its own tiny mass. The effects are far too small to feel in a spring or a warm cup. The speed of light is so large that everyday energies translate into masses far below anything a kitchen scale could catch. But in the deep interior of matter, where energies run high and particles are bound together with tremendous force, this conversion stops being a rounding error and becomes the main event. There, energy wearing the coat of mass can outweigh the actual particles by a wide margin. Hold that thought against the puzzle from the first chapter. The proton weighs far more than its quarks added up. Now we have the reason such a thing is even possible. The extra weight does not have to come from more particles. It can come from energy, bound and trapped inside the proton, counted as mass by Einstein's relation. The stuff in your hand can weigh more than its pieces, because some of the weight is not pieces at all. It is energy, locked in place. This is the first crack in the simple add-up-the-parts picture, and it is a wide one. Mass is no longer just a count of how much matter there is. It is a measure of energy in all its forms, the resting energy of particles and the binding energy that holds them together. Two of those will turn out to matter for our story, and they have completely different sources. One kind of mass is the energy a particle has just by existing, even at rest. The other kind is the energy stored in the forces between particles. The Higgs field, when we reach it, will speak only to the first kind, the resting mass of the fundamental particles. The second kind, the binding energy, belongs to a different force entirely, the strong force that grips the quarks. Most of the weight in your hand lives in that second kind. Einstein's relation is what lets us see it as mass at all. So the Patent-Clark's short equation did something Newton's laws never tried to. It opened a door between mass and energy and showed they were the same currency. It did not yet say where any particular particle's mass comes from, but it changed the shape of the question, from how much matter is there to how much energy is bound up, and in what form. With that door open, we can finally ask the question this whole story turns on. We can now say plainly what we're after. Newton told us what mass does, how it resists a push, and answers to gravity. Einstein told us that mass and energy trade places, that one can become the other. Neither of them asked the question that sits underneath both. Why does anything have mass in the first place? Why is the number not simply zero? That question only sharpens when you look at the smallest particles we know. A particle like the electron has a definite mass, a small but fixed amount of resistance to being pushed. It is not made of smaller pieces as far as anyone has ever found. You cannot explain its mass by adding up parts, because there are no parts. The mass is just there, a property of the electron itself, the way its electric charge is just there. So where does that property come from? For a long time, the honest answer was that no one knew, and stranger still, the best theory of particles seemed to say the number should be zero. This is the part that surprises people. The deepest framework physicists built for the particles and forces, the one we will come to call the Standard Model, works most cleanly when its particles have no mass at all. Massless particles fit the math beautifully. The moment you try to give them mass by hand, the equations break. That is a strange place to land. The theory that describes the world better than any before, it preferred a world where nothing weighs anything. But things plainly do weigh something. The electron has mass. The particles that carry one of the forces, the W and Z, are heavy. The world is full of mass, and the best theory of it, left to its own rules, says there should be none. Something had to bridge that gap, some new ingredient that lets mass exist without breaking the beautiful math underneath. That ingredient is the heart of this story. It is not a particle in the ordinary sense, not at first. It is a field, a thing spread through all of space, present even where there is nothing else. The famous Higgs boson is a ripple in that field, the sign that the field is really there. But the field is the main character, and the mass it gives is one particular kind, the resting mass of the fundamental particles that have no parts. So we are chasing two different mysteries that the word mass quietly bundles together. The first is the mass of the truly fundamental particles, the electron and the quarks and the heavy force carriers, the particles with no smaller pieces inside. That is the mass the Higgs field will explain. The second is the mass of the things those particles build, the protons and neutrons, and therefore the stone in your hand. That mass, as we have started to see, comes mostly from bound energy, not from the Higgs at all. The trouble in the title lives in the space between those two. People hear that the Higgs gives the universe its mass, and they picture it explaining the weight of everything, the stone, the mug, their own body. It does not. It explains a real and important slice, the mass of the fundamental particles. But that slice is a small fraction of the mass of ordinary matter. The Higgs solved a genuine problem and left a larger one standing, and the larger one was solved by something else. To see all of this clearly, and to understand why it is not a flaw but simply how the layers stack, We have to meet the particles themselves. We need to know which ones are fundamental and which are built, which ones get their mass from the field and which get it from a force. We need the cast of characters before the plot can move. So the next step is a careful look at the particles the standard model is made of. Not all of them carry mass, and the ones that do carry it for different reasons. Sorting that out is what turns a famous slogan into a real understanding. The standard model is the best map we have of the smallest pieces of the world. It was built over decades, through the middle and later 20th century by many hands, and it sorts the fundamental particles into a small, tidy chart. Fundamental here means a particle with no smaller parts inside, as far as any experiment has shown. These are the genuine building blocks, the ones whose mass cannot be explained by adding up pieces. There are two great families. The first is the matter particles, called fermions, the ones that make up the stuff around you. Among them are the quarks, which come in 6 kinds, with names chosen for fun more than meaning: up, down, charm, strange, top, and bottom. The up and down quarks are the ones that build the protons and neutrons in every atom. Then there are the leptons, a second set of 6, which includes the familiar electron and its heavier cousins, the muon and the tau, along with 3 faint particles called neutrinos. The second family is the force carriers, called bosons. These are the particles that carry the forces between the matter particles, the messengers that let one particle feel another. The photon carries the electromagnetic force, the force of light and magnetism, and the bond between atoms. The gluon carries the strong force which binds quarks together. The W and Z particles carry the weak force, which drives certain kinds of radioactive decay and helps power the sun. Now look at which of these carry mass, because the pattern is the whole point. The quarks have mass, and it ranges wildly. The up and down quarks are very light. The top quark, the heaviest of all the fundamental particles, is staggeringly heavy, weighing as much as a whole atom of gold despite being a single point with no size. The charged leptons have mass too, with the electron light, the muon about 200 times heavier and the tau heavier still. The neutrinos have mass as well, but a tiny ghostly amount we will return to later. Among the force carriers, the picture splits sharply. The photon has no mass at all, the gluon has no mass either, but the W and Z particles are heavy, each weighing nearly as much as a medium-sized atom, which is enormous for a single force carrier. So within one family, 2 messengers weigh nothing and 2 weigh a great deal. That split is not a minor quirk. It is one of the loudest clues in all of physics, and the search for its cause is what led to the Higgs. Stand back, and the question comes into focus. The standard model has a list of particles and a list of their masses, and those masses span an extraordinary range, from the weightless photon to the gold-heavy top quark. Why this pattern? Why are some carriers massless and others heavy? Why does the top quark outweigh the electron by a factor of hundreds of thousands? The standard model as a chart simply records these numbers. It does not by itself say where they come from. And recall the deeper trouble from before. The math of the model works most cleanly when every one of these particles has no mass. Massless quarks, massless leptons, massless W and Z. In that pristine version, the equations have a beautiful balance to them. The masses we actually measure spoil that balance if you just write them in by hand, so the model faces a demand. It must find a way to let these particles be heavy while keeping the underlying balance intact. That balance has a name, and understanding it is the next step. It is called symmetry, and in physics, symmetry is not just about things looking the same when flipped or turned. It is the hidden rule that decides which forces can exist and how they must behave. The reason the photon must be massless, and the reason the W and Z seem like they should be too, both come from a particular kind of symmetry woven into the forces themselves. In ordinary talk, symmetry means a kind of sameness. A face is symmetric when its left matches its right. A snowflake is symmetric when you can turn it and it looks unchanged. The heart of the idea is this. You do something to a thing, and afterward it looks exactly as it did before. The change leaves no trace. Physics took that idea and made it one of its deepest principles. A physical law is symmetric when you can change something about your description of the world, and the law still reads the same. Move your whole experiment 10 meters to the left, and the laws of physics do not care. Run it tomorrow instead of today, and they do not care. These sameness under change rules turn out to be tied, by a precise mathematical thread, to the things that never change in nature, the quantities that are conserved, like energy and momentum. There is a special, more abstract kind of symmetry that runs the forces, and it is called gauge symmetry. To get a feel for it, think of measuring height. You can measure the height of a building from the street, or from the floor of its basement, or from sea level. The number you write down changes with your choice, but the building does not change at all, and the physics of standing in it does not change. The choice of where to set zero is yours, a convention, and nothing real depends on it. Gauge symmetry says something like that about certain hidden properties of particles. Each particle carries internal labels, a bit like a phase or an angle, that you cannot observe directly. Gauge symmetry is the statement that you are free to redefine those labels, even differently at every point in space and every moment in time, and the physics must come out the same. Nature does not care about your bookkeeping for these hidden labels, any more than the building cares where you put the zero of your ruler. Here is the remarkable part, the part that turns a bookkeeping rule into the source of forces. If you demand that freedom, that you can reset the hidden labels anywhere, any time, with no effect on the physics, the equations do not stay simple on their own. They only hold together if you add something new, a field that reaches across space to keep the accounts consistent from place to place. That added field is a force. The demand for gauge symmetry forces a force into existence. This is one of the most beautiful results in all of physics. The electromagnetic force, the one carried by the photon, comes from exactly this kind of demand applied to one hidden label of charged particles. Insist that you can redefine that label freely everywhere, and out drops the entire theory of electricity and magnetism, photon and all. The strong force and the weak force come from the same move applied to other, richer sets of hidden labels. Forces are not added to the particles from outside. They are the price of demanding this freedom, and they are the means by which nature pays it. So gauge symmetry is the hidden rule behind the forces. It is why the forces exist, why they take the precise shape they do, and why their carriers behave as they behave. The Standard Model is, at its core, a careful statement of which gauge symmetries the world obeys, and the photon, the gluon, and the W and Z all spring from that statement. But this gift comes with a string attached, and the string is the knot at the centre of our story. The same gauge symmetry that conjures the forces also seems to insist on something we know is false. It demands, when you follow the math through, that the force carriers have no mass. For the photon and the gluon, that is fine, because they truly are massless. For the W and Z, which are heavy, it is a flat contradiction. The next step is to see exactly why the symmetry seems to forbid mass, and why that forbidding is so hard to escape. Why would a symmetry forbid mass? The answer takes a little care, but it rests on something you can picture. A massless particle and a massive one differ in a way that goes beyond weight, in how they can move and turn in space, and gauge symmetry is fussy about exactly that difference. Start with the photon, the carrier of the electromagnetic force, which truly has no mass. A massless particle always moves at the speed of light. It can never be slowed, never be brought to rest, never be caught up with. Because it can never sit still, it has fewer ways to be oriented than a massive particle does. A photon's wave can wiggle in only two independent directions, both crosswise to its motion. It has, in the physicists' counting, two states of polarization, and no more. Now think of a massive force carrier like the W. Because it has mass, it can be slowed down and even brought to rest, and once you can stand still beside it, you can look at it from any angle, which gives it an extra way to be oriented that the photon does not have. A massive carrier has 3 independent states, not 2. That extra state, the third one, is the troublemaker. It is the spare part that the massless theory has no room for. Gauge symmetry, the rule that conjures the force in the first place, is built around the 2-state massless kind of carrier. The whole beautiful machinery, the freedom to reset the hidden labels everywhere, works precisely because the carrier has only those 2 crosswise states. Try to give the carrier a mass directly, by writing a mass term into the equations by hand, and you suddenly need that third state, and the gauge symmetry breaks. The accounts no longer balance from place to place. The theory loses the very property that made it work, and it starts coughing up nonsense, infinite answers where there should be finite ones. This is the massless rule, and it is not a soft suggestion. It is baked into the structure. A gauge force taken at face value comes with a massless carrier, or it does not come at all. The photon obeys this happily. So does the gluon, the carrier of the strong force, which is also massless. For these two, the symmetry and the world agree, and there is no problem to solve. The weak force is where the agreement shatters. Everything about the weak force says it should be a gauge force, cut from the same cloth as electromagnetism. The math wants it to be. But the weak force has a strange property that sets it apart. It is feeble and short-ranged, reaching only across a distance far smaller than an atomic nucleus, while electromagnetism reaches across the whole universe. And there is a clean reason a force would be short-ranged. Its carrier is heavy. A heavy carrier cannot travel far, so the force it brings dies away quickly. The short reach of the weak force is a fingerprint of massive carriers. So physicists were caught between 2 truths that would not sit together. The symmetry that makes the weak force work demands a massless carrier. The behavior of the weak force in the real world demands a heavy one. The W and Z had to be massive, and the math said they could not be. You could not simply write the mass in by hand without wrecking the theory, the same way you cannot wedge that third state into a structure with no room for it. For years this was a genuine wall. The most promising framework for the weak force kept producing massless carriers that did not match reality, or, when forced to be massive, produced gibberish. The puzzle was not how to measure the masses. The puzzle was how a mass could exist at all, without tearing down the symmetry that gave the force its life. The way through would come from an unexpected place, far from particle physics, in the cold, quiet behavior of metals chilled almost to the bottom of the temperature scale. Let me put real flesh on these heavy messengers, because they are the particles that force the whole question into the open. The weak force they carry is the quietest of the 4 forces in daily life, yet without it the sun would not shine. It is the force behind one particular kind of radioactivity, where a neutron inside a nucleus turns into a proton, spitting out an electron and a ghostly neutrino. That slow transformation, called beta decay, is the weak force at work, and it is also the first step in the chain that lets the sun fuse hydrogen and pour out light. For a long time, the weak force was known only by what it did, not by what carried it. By the 1960s, 3 physicists working separately, Sheldon Glashow, Steven Weinberg, and Abdus Salam, had woven the weak force together with electromagnetism into a single framework, now called the electroweak theory. It was a stunning unification, treating 2 forces that look completely different as 2 faces of one deeper thing, and it made a sharp prediction. The weak force had to be carried by 3 particles, 2 of them electrically charged, named W plus and W minus, and 1 neutral, named Z. The theory even predicted, once the mechanism we are building toward was in place, roughly how heavy these carriers should be. They were expected to be very massive, far heavier than a proton, which is why the weak force is so feeble and so short of reach. A heavy carrier is a sluggish messenger. It can only flit out and back across a tiny distance before it must vanish, so the force it carries cannot reach beyond the width of a nucleus. The faintness of the weak force in your everyday life is the direct shadow of how heavy its carriers are. Finding them was a monumental task because making such heavy particles takes enormous energy, packed into a tiny space. That energy was reached at CERN, the great European laboratory near Geneva, in the early 1980s. A machine smashed protons into their antimatter twins, antiprotons, head-on, concentrating the collision energy enough to conjure the heavy carriers for the briefest of instants. In 1983, 2 experiments there, led in large part by the physicist Carlo Rubbia, caught the W and then the Z in the debris. The predicted particles were real. When their masses were measured, the numbers were striking. The W weighs about 80 times as much as a proton. The Z is heavier still, about 91 times a proton's mass. For single-force carriers, that is staggering. The photon, doing the same kind of job for electromagnetism, weighs exactly nothing. Set the 2 side by side, the weightless photon and the gold-heavy Z, and you're staring straight at the puzzle. These particles are siblings in the electroweak family, born of the same symmetry, and yet one is massless and the others are enormous. That contrast is the rule breaker. If the symmetry truly demanded massless carriers, the W and Z should have weighed nothing, like the photon. They do not. They are among the heaviest particles we know. Something gave them mass without destroying the electroweak theory, because the theory, mass and all, makes predictions that match experiment to remarkable precision. The masses were not written in by a clumsy hand. They came from somewhere that left the symmetry quietly intact underneath. So the W and Z are not just 2 more particles on the chart. They are the evidence that mass can appear in a gauge theory, in a way the naive rule forbids, and yet not break it. They are proof that there is a gentler path, a way for the symmetry to be present in the equations and hidden in the world. Finding that path was the breakthrough, and the first glimpse of it did not come from smashing particles together at all. It came from a humble, well-studied fact about certain metals that when you cool them far enough, they lose all resistance to electric current, and in doing so, do something to light itself. Cool certain metals down to nearly the coldest temperature there is, a few degrees above the absolute bottom, and something remarkable happens. Their resistance to electric current does not just shrink, it vanishes completely. A current set flowing in a loop of such metal will circle on and on for years without fading. These materials are called superconductors, and they were a deep puzzle of their own for decades before they quietly handed particle physics its answer. What matters for our story is a particular trick a superconductor plays on magnetic fields. Try to push a magnetic field into a superconductor, and it refuses entry, expelling the field from its interior. If some field does get in, at the edges, it cannot reach far. It dies away over a tiny distance and goes no deeper. The magnetic field, which in open space reaches across a room with ease, is suddenly short-ranged inside the metal, snuffed out after the thinnest sliver. A physicist looking at that behaviour in the language of fields would describe it in a striking way. Inside the superconductor, the field that carries magnetism acts as though it has become heavy. A short reach is the signature of a heavy carrier, just as we saw with the weak force. The photon, weightless and far-reaching out in the open, behaves inside the superconductor as if it had gained a mass, and that gained mass is exactly why the magnetic field cannot push through. Sit with how strange that is. The photon has no mass. It is the very picture of a massless particle. Yet here, inside a cold lump of metal, it moves as though it weighs something. Nothing changed the photon itself. What changed was the stuff it was moving through. The superconductor is filled, below its critical temperature, with a kind of condensed sea of paired electrons, and the photon ploughing through that sea is slowed and shortened exactly as a massive carrier would be. The mass is not built into the photon. It is handed to the photon by the medium. This was the clue. In the early 1960s, the physicist Philip Anderson, who knew superconductors as well as anyone alive, saw what it might mean for the larger puzzle. The lesson was that a force carrier could behave as massive without you ever writing a mass into the underlying law. You did not have to break the beautiful symmetry by hand. You only had to fill space with the right kind of medium, and the carrier moving through it would act heavy, all on its own, while the deep symmetry of the equations stayed untouched beneath the surface. Anderson pointed out that this was precisely the kind of thing the particle physicists needed. Their problem was that gauge symmetry forbade them from giving the W and Z a mass directly. The superconductor showed a side door. Do not give the carriers mass. Instead, fill all of space, even empty space, with a medium like the C inside the superconductor, and let the carriers gain their mass by moving through it. The symmetry would still be there in the laws. It would simply be hidden by the medium that fills the world. That was the seed of the whole idea. Empty space, the vacuum itself, might not be truly empty. It might be filled everywhere with a field, a medium of its own, and the particles we call massive might be the ones that interact with it, slowed and weighed down as they move, while the massless ones, the photon and the gluon, simply ignore it and pass through untouched. Anderson had the physical picture, drawn straight from cold metal, but the full working version for the particle world, written in the proper language of the forces and made to fit the gauge symmetry exactly, still had to be built. That construction came in a single remarkable year, from several groups of physicists working at nearly the same time, mostly unaware of one another, all reaching for the same door Anderson had pointed to. The year was 1964, and the idea arrived not once but 3 times over, from 3 groups working apart. This kind of near-simultaneous discovery happens now and then in science, when a problem is ripe, and the tools to crack it have all quietly come into place. The way out of the mass puzzle was ready to be found, and several careful minds found it within months of one another. The first paper came from 2 physicists in Belgium, Robert Brute and François Engler, working together at the Free University of Brussels. They wrote down a way for a gauge force carrier to acquire a mass while keeping the underlying symmetry of the equations intact, building directly on the kind of insight Anderson had drawn from superconductors. Their work was the earliest of the 3 to appear in print that year. Close behind, working alone in Edinburgh, came Peter Higgs. He arrived at the same mechanism by his own path, and he added something the others had not stressed as sharply. He pointed out that this field filling all of space should have its own particle, a ripple in the field that could in principle be made and detected. That particle is the one that now carries his name, the Higgs Boson. Higgs nearly did not get the point published. An early version of his note was turned down by a journal for failing to make clear why it mattered, and he revised it, sharpening it to highlight that very prediction of a new particle before it was accepted. The third group was a trio in London, Gerald Guralnick, Carl Hulgan and Tom Kibble, working at Imperial College along their own line of reasoning. They produced the most mathematically complete treatment of the 3, tying up loose ends the others had left, and they published just after the first 2, having developed their version largely without knowing the others were so close. So 6 physicists, in 3 papers, across a single year, independently opened the same door. The mechanism they described goes by several names, depending on who is being honoured, but it is most often called the Higgs mechanism, after the man who most clearly tied it to a findable particle. It is worth holding all the names, though, because the idea was a shared achievement, not a lone stroke. The history is a reminder that big steps often come from many hands reaching at once. What did these papers actually say? In plain terms, they propose that all of space is filled with a new field, present even in the emptiest vacuum, and that this field has settled into a state that quietly hides the symmetry of the forces without destroying it. The W and Z moving through this field are slowed and weighed down, gaining their large masses, while the photon ignores the field and stays massless. The symmetry is still there in the deep equations. It is simply not visible in the world the field has shaped, the way a clue can be present in a room without being noticed. For years, this was a beautiful idea with no proof. It explained how the W and Z could be heavy, and it fit neatly into the electroweak theory of Glashow, Weinberg, and Salam, which leaned on it to make its predictions work. When the W and Z were found in 1983 with just the masses the theory expected, the mechanism looked very likely to be right. But the field itself and its telltale particle had not been seen. The boson Peter Higgs had predicted remained hidden, and finding it would take nearly half a century and a machine larger than any built before. The recognition came in time. In 2013, the year after the boson was finally found, the Nobel Prize in Physics went to Peter Higgs and François Englert for the prediction. Robert Brute had died 2 years earlier and could not share it. To understand what they predicted, though, we need to look closely at the strange way this field hides asymmetry, because that hiding is the true engine of the whole mechanism. The key idea has a forbidding name, spontaneous symmetry breaking, but the picture behind it is something you have seen many times. It is what happens when a system that is perfectly balanced settles, on its own, into a state that is not. The balance was real. The settling is real. And after the settling, the original balance is hidden, present in the rules but invisible in the result. Picture a pencil balanced perfectly on its sharp tip, standing straight up. In that instant, it has a lovely symmetry. Every direction around it is exactly the same. There is no reason for it to lean north rather than south, east rather than west. The setup does not prefer any direction, but that balance cannot last. The pencil will fall, and when it falls it must pick a direction, one single way to point. The moment it lands, the perfect sameness of all directions is gone. The pencil now points one way. Here is the subtle part that makes this the right picture. The laws that govern the pencil never preferred a direction. They are still perfectly even-handed, the same toward every point of the compass. The symmetry of the laws is untouched. What broke was not the law, but the outcome. The pencil had to land somewhere, and in landing it chose, and the choice hid the underlying sameness. The symmetry is spontaneously broken, meaning the system broke it by itself, just by settling into one of its many equally good resting states. Now carry that idea from a pencil to a field that fills all of space. A field, in physics, is just a quantity that has a value at every point, like the temperature in a room or the depth of water across a pond. The Higgs field is such a quantity, spread everywhere. The question is what value it settles into in empty space, when nothing is disturbing it, when it is left alone at the lowest energy it can find. You might expect the lowest energy to be at a field value of 0. The field simply switched off, nothing there. For most fields that is exactly right. The empty vacuum is the field set to 0, quiet and blank. If the Higgs field were like that, settling to 0, it would do nothing, and particles passing through empty space would feel nothing, and there would be no mass to explain. The whole mechanism depends on the Higgs field being different. The Higgs field is built so that its lowest energy is not at 0. Switched off, at 0, it actually sits at a little hump of energy, an unstable perch like the pencil on its tip. To reach its true resting state, the lowest energy available, the field has to take on a value that is not 0, the way the pencil has to fall to lie down flat. So in empty space, with nothing disturbing it, the Higgs field does not settle to nothing. It settles to a definite non-zero value, the same everywhere, filling the vacuum with a steady humming presence. That is the crucial move. The vacuum, the emptiest space there is not empty of the Higgs field. It is full of it, at a fixed non-zero level, because that is where the field's energy is lowest. And just as the fallen pencil hides the evenness of all directions, the settled Higgs field hides the symmetry of the forces. The deep equations still have their full symmetry. The world built on top of the settled field does not show it. The symmetry is there and hidden, exactly the trick the W and Z needed. To make this picture sharp, physicists draw the field's energy as a shape, a landscape with hills and valleys, where the field rolls downhill to settle in the lowest valley. The particular shape of that landscape is what forces the field away from 0. It is one of the most famous shapes in physics, and it looks, fittingly, like the bottom of a wine bottle. Imagine drawing a graph of the Higgs field's energy. Along the bottom you mark the value of the field, how strong it is. Up the side you mark how much energy the field has at that strength. For most fields, this graph is a simple bowl, lowest in the very middle, at a field value of 0 and rising on both sides. The field rolls to the bottom of the bowl, which sits at 0, and there it rests, switched off. That is an ordinary empty vacuum. The Higgs field's graph is shaped differently, and the difference is everything. Instead of a simple bowl with its low point in the centre, it has a small bump pushed up in the middle and a circular trough running around it, like a gutter at the base. Spun into its full three-dimensional form, this shape looks just like the punt at the bottom of a wine bottle, the glass dome that rises in the centre with a ring-shaped valley around its foot. Physicists often call it the wine bottle potential, or, with a nod to a certain hat, the Mexican hat. Now ask where the field will settle. It rolls to the lowest energy it can find, the way water runs to the lowest point of a surface. In this shape, the centre, at field value 0, is not the lowest point. It is the top of the little bump, a perch, like the pencil on its tip. The true lowest points lie all around, down in the circular trough. So the field cannot rest at 0. It must roll off the central bump and come to rest somewhere down in the ring, at a definite non-zero strength. The vacuum fills with the field at that value. This is the precise reason the Higgs field is present in empty space rather than switched off. Its energy landscape simply has no resting place at 0. The lowest energy, the most peaceful state available, the one the universe falls into and stays in, is a state where the field is on, humming everywhere at a fixed strength. Empty space is the trough of the wine bottle, and the field has rolled down into it and settled. The shape also explains the symmetry and its hiding in one stroke. Look at the trough. It is a perfect circle. Every point along it is the same height, the same lowest energy, so the field could settle at any point around the ring with equal ease. That circular sameness is the symmetry, alive and intact in the shape itself. But the field, when it settles, has to pick one spot in the trough, just one, the way the pencil picks one direction to fall. The instant it picks, the circular sameness is hidden. The law, the shape, stays perfectly round. The outcome, the chosen spot, does not. There is a real consequence to which way the field can move once it is settled, and it matters for what comes next. From its chosen spot in the trough, the field can be nudged in two different ways. It can be pushed around the circle along the flat bottom of the gutter, which costs almost no energy because the trough is level all the way around, or it can be pushed up the steep inner wall toward the central bump, which costs a great deal of energy. These two directions, the easy one and the hard one, will turn out to correspond to two very different things, one of which is swallowed up to give the W and Z their mass, and the other of which becomes the Higgs boson itself. For now, hold the shape in mind because it is the heart of the mechanism. A field whose energy is lowest, not at 0, but in a ring around it, so that empty space is forced to fill with the field at a steady strength. That filled vacuum is what every particle moves through, all the time, everywhere. The next step is to take that picture seriously and ask what it means to say a field is really there, in the vacuum, in the gaps between the stars, in the space inside your own body. We use the word field loosely in daily life, so it helps to be plain about what physicists mean by it. A field is a quantity that has a value at every point in space. The temperature in a room is a field. At each spot you could place a thermometer and read a number, and those numbers together, all through the room, are the temperature field. A field is not a thing sitting at one place. It is a value spread across all places, defined everywhere at once. The fields of particle physics are like that, but deeper. In the modern view, every kind of particle is really a ripple in a field that fills all of space. There is an electron field stretched through the whole universe, and an electron is a little travelling disturbance in it, a packet of ripple moving along. There is a field for each kind of quark, a field for the photon, and so on. The particles you think of as tiny balls are better understood as waves in these everywhere fields. This is the picture that the most successful theory of matter, called quantum field theory, is built on. The Higgs field is one more of these, with one crucial difference we have just seen. The other fields, left undisturbed in empty space, settle to zero. Their vacuum is blank, the field switched off, and a particle appears only when something stirs up a ripple. The Higgs field does not settle to zero. Its energy landscape, the wine bottle shape, forces it to rest at a non-zero value, even when nothing is disturbing it. So the Higgs field is on, everywhere, all the time, in the deepest vacuum, at a steady strength that never lets up. Take that seriously, and the picture of empty space changes. The space between the stars, the gap inside an atom, the room around you when the air is pumped out, none of it is truly empty. It is all filled with the Higgs field, humming at its fixed value, a smooth, invisible presence with no edges and no gaps. You are immersed in it right now. It passes through you and through everything, the same in here as out in the void between galaxies. There is nowhere you can go to escape it, because there is nowhere it is not. This is a genuinely new kind of emptiness, and it is worth pausing on, because it overturns an old and natural assumption. We tend to think of the vacuum as nothing, as the absence of all things, the blank stage on which matter acts. The Higgs field says the stage is not blank. The lowest energy state of the universe, the closest thing there is to nothing, still has this field present in it at full strength. Empty space has a property, a value, a hum, built into its very floor. How can we believe such a thing is real when we cannot see it or feel it directly? The answer is the same as for anything in physics. We believe it because it explains what we measure, and because it predicts something new that then turns out to be there. The filled Higgs field explains why the W and Z are heavy, and the photon is not, matching their masses precisely. And it predicted a particle, the ripple in this field that Peter Higgs pointed to, which was found in 2012 at exactly the kind of energy the theory needed. A field you cannot see, confirmed by a particle you can make. So the Higgs field is not a metaphor or a way of speaking. It is a real physical field, as real as the electric field that makes your hair stand up, or the magnetic field that turns a compass needle. And it is present in every cubic centimetre of the universe at a fixed, unchanging strength. The next question is the one everyone asks the moment they hear this. If empty space is full of this field, how exactly does moving through it give a particle mass? The usual quick answer is a comparison to wading through something thick, and it is worth telling carefully, both for where it helps and for where it quietly misleads. Here is the comparison you've probably heard. Empty space is full of the Higgs field, like a tank full of honey or thick syrup. A particle moving through it is like a spoon dragged through the honey. The honey resists the spoon, slows it, makes it harder to push, and that resistance is what we call mass. Particles that interact strongly with the field feel a lot of drag and end up heavy. Particles that barely interact or not at all slip through and stay light or massless. That picture gets one thing right, and it is the most important thing. Mass, in this story, is about interaction with the field that fills space. A particle is heavy because of how it couples to the Higgs field, not because of any stuff packed inside it. The W and Z are heavy because they interact strongly with the field. The photon is massless because it does not interact with the field at all and passes through as if it were not there. So far the honey serves us well. But push on the comparison and it breaks in a way worth understanding, because the break reveals the real physics. Drag in honey slows a moving spoon down. Keep dragging and the honey will bring the spoon to a stop. If mass really were honey drag, a moving particle would steadily lose speed and halt, and a particle sitting still would feel nothing at all, since there is no drag without motion. Neither of those is true. A massive particle in empty space does not slow down on its own. Set it moving and it coasts forever, exactly as Newton said. And a particle at rest still has its mass, its resistance to being pushed, even though it is not moving through anything. So the Higgs field is not a drag that opposes motion. It does not act like honey at all in that respect. What it does is more subtle. By interacting with the field that fills the vacuum, a particle gains the very property of resisting changes in its motion, which is to say it gains mass, the inertial mass we met long ago, the stubbornness against being pushed. The field gives the particle that stubbornness whether it is moving or still. It does not sap a moving particle's speed. It gives the particle a mass it then carries everywhere, the same at rest as in motion. There is a cleaner way to picture the real effect, though no everyday image is perfect. Without the field, certain particles would be like the photon, forced to fly at the speed of a light, unable ever to slow or stop, with no rest and no resting mass. Interacting with the filled Higgs field is what lets such a particle move slower than light, to be brought to rest, to have a settled mass it owns at all times. The field does not drag the particle down, it anchors the particle into the slower, heavier world of things that can sit still. This matters because the honey image, taken too far, plants a wrong idea, that mass is friction, a resistance that eats motion. Mass is not friction. A planet orbits for billions of years without the Higgs field slowing it by a hair. The field's gift is the mass itself, the fixed quantity of resistance to a push, not an ongoing drag that opposes movement. Keep the part of the comparison that is true, that mass comes from interaction with a field filling all of space, and set aside the part that misleads, the idea of a slowing drag. With that cleared up, one question remains, and it is the sharpest one yet. If every massive particle gets its mass by interacting with the same single field, why do their masses differ so wildly? The top quark and the electron swim in the very same Higgs field, yet one is hundreds of thousands of times heavier than the other. The field is one thing, the same everywhere. The masses are all over the map. The answer is a single dial set differently for each particle, and that dial is where we turn next. Every massive particle swims in the same Higgs field, the one field filling all of space at its fixed strength. Yet their masses run across an enormous range, from the feather-light electron to the gold-heavy top quark. If the field is one and the same for all of them, the difference cannot come from the field. It must come from the particles, from how each one relates to the field it moves through. That relation has a name. Physicists call it coupling, and it is simply how strongly a given particle interacts with the Higgs field. Think of it as a dial, set to a different number for each kind of particle. Turn the dial high and the particle grips the field tightly, interacts with it strongly, and comes out very heavy. Turn the dial low and the particle barely engages the field, interacts only weakly, and comes out very light. Turn it all the way to zero, as for the photon, and the particle ignores the field completely and has no mass at all. The mass of each fundamental particle is just its coupling to the Higgs field, times the fixed strength of the field in the vacuum. The field strength is the same for everyone. The coupling is the part that varies. So the top quark is the heaviest fundamental particle because its dial is turned up the highest, gripping the field harder than anything else. The electron is light because its dial is turned far down. The neutrinos, lightest of all the massive particles, have dials turned almost to nothing. One field, many dials, and the spread of masses follows. This is a real and satisfying piece of understanding. It tells us the shape of the answer. Mass, for a fundamental particle, is a matter of how strongly it couples to a field that is everywhere. The W and Z couple strongly and are heavy. The photon does not couple and is massless. The whole confusing range of fundamental masses comes from this one mechanism, a single field and a set of coupling strengths, and it fits the measured numbers when the dials are set to match. But notice what this explanation does and does not do, because the gap between the two is the quiet heart of the title's trouble. The Higgs mechanism explains how a fundamental particle can have mass at all, where before the symmetry forbade it. It gives the structure, the machinery, the reason mass is possible without breaking the deep equations. What it does not do is say why the dials are set where they are. It does not predict the electrons' coupling, or the top quarks, or any of them. Each dial is measured, then fed into the theory by hand. The mechanism takes the masses as input. It does not explain their values, so the Higgs field tells us the form of the answer but not the numbers. It is like learning that every coin in a jar was set by turning a knob, which is real knowledge, while still having no idea why each knob was turned to its particular spot. The mechanism is sound and confirmed. The specific masses remain unexplained, a set of numbers the universe simply hands us, and the spread between them, from the lightest to the heaviest, is one of the open puzzles we will come back to. There is a second, larger gap, and it is the one the title is really pointing at. Everything we have built so far concerns the fundamental particles, the ones with no parts, the quarks and leptons and heavy carriers. Their mass comes from the Higgs field through these coupling dials. But the mass you actually hold in your hand, the weight of the stone, lives almost entirely in protons and neutrons, and those are not fundamental. They are built from quarks bound by the strong force. When we weigh them, the Higgs turns out to account for almost none of it. To see where the rest comes from, we have to leave the Higgs field behind for a while and go inside the proton. Go back to the wine bottle shape one more time, because it hides the boson inside it. Recall that once the Higgs field settles into the circular trough, it can be nudged in two ways. It can be pushed around the flat bottom of the ring, which costs almost no energy, or it can be pushed up the steep inner wall toward the central bump, which costs a great deal. Those two directions are not just geometry. Each one corresponds to a real physical thing in the world, and telling them apart is how the Higgs boson was predicted. Start with the easy direction, around the ring. A field that can be shifted at almost no energy cost behaves like a particle with almost no mass. The mechanism produces these easy direction ripples, and at first they look like a problem, extra massless particles that we do not see in nature. But this is where the gauge symmetry pays off in a beautiful way. Those easy ripples do not stay free. They are absorbed by the W and Z, becoming exactly the third state of motion that a massive carrier needs and a massless one lacks. The easy direction of the Higgs field is swallowed to make the W and Z heavy. It does not survive as a particle of its own. Now the hard direction, up the steep wall toward the central bump. Pushing the field that way costs real energy, and a field that resists being moved, that springs back when displaced, behaves like a particle with mass. This stiff, hard-to-move ripple is not swallowed by anything. It survives. It is a real particle, a vibration of the Higgs field along its steep direction, and that particle is the Higgs boson. Its existence is not an optional extra. If the field is really there, filling space and settled in its trough, then it must be able to ripple along the steep wall, and that ripple must show up as a particle you can make and detect. This was Peter Higgs's sharpest contribution in 1964. The mechanism filled space with a field and gave the carriers their mass, and Higgs pointed out that the same field, by its very nature, demanded a new particle. The field could not be present without the boson being possible, so the boson became a test. Find it, and you confirm the field is real. Fail to find it, after looking hard enough in the right place, and the whole picture would be in serious trouble. The boson's mass, though, the theory could not predict. The energy cost of climbing that steep inner wall depends on the exact steepness of the wine bottle shape, and that steepness was not fixed by the theory. So physicists knew a Higgs boson should exist, and knew many of its properties, how it should be made and how it should decay, but they did not know how heavy it would be. That single unknown number turned the search into a long hunt, across a wide range of possible masses, each one needing more energy to reach than the last. There was one more reason the boson mattered so much. Everything else in the Higgs story was indirect. The masses of the W and Z fit. The electroweak theory worked. The field explained the pattern, but no one had touched the field itself. The boson was the one piece you could actually produce in a machine and see in a detector. The field made briefly tangible. Until it appeared, the filled vacuum remained a powerful idea that fit the evidence without being directly confirmed. So by the late 20th century, physics had a clear and pressing assignment. Build a machine powerful enough to shake the Higgs field hard enough to make a ripple climb its steep wall, and catch that ripple before it vanished. The boson would not last. It would decay almost the instant it formed, into a spray of lighter particles. Finding it would mean reading those sprays, sifting countless collisions for the faint, particular signature of the field briefly made real. That hunt would stretch across decades and several great machines. The search did not begin with the machine that finally succeeded. It began with earlier accelerators that slowly closed off the places the Higgs boson could be hiding. Because the theory could not say how heavy the boson was, physicists had to sweep across a wide range of possible masses, and each machine could reach only so far. The story of the hunt is really the story of that range narrowing, year by year, from both ends. The first great effort was at CERN in a machine called LEP, the Large Electron-Positron Collider, which ran through the 1990s in a circular tunnel 27 kilometers around, buried beneath the border of France and Switzerland. LEP smashed electrons into their antimatter partners, positrons, and among everything else it studied, it searched for the Higgs. It never found one, but a search that comes up empty is not a search that comes up useless. By not seeing the boson, LEP could rule out the lighter masses where it would have been easy to make. If the Higgs had been that light, LEP would have produced it. So the lower end of the range was closed off. By the time LEP shut down in the year 2000 to make room in its tunnel for a far more powerful machine, it had pushed the boson's possible mass upward, establishing that if it existed, it had to be heavier than a certain floor. There was even a flicker of excitement in LEP's final months, a faint hint that something might be appearing right at the edge of its reach, but the data were not strong enough to claim a discovery, and the machine was closed on schedule. The hint faded. The hunt moved on. The next push came from across the Atlantic at Fermilab near Chicago, where a machine called the Tevatron collided protons with antiprotons at higher energy than LEP could reach. Through the early 2000s, its two experiments hunted the Higgs in the middle range of masses, where LEP could not look. The Tevatron never quite caught the boson either, but it too narrowed the field, chipping away at the middle of the range and excluding a band of masses where the boson was not found. Between LEP from below and the Tevatron through the middle, the open territory was shrinking. What both machines showed, in the negative, was where to look next. The boson was not light, or LEP would have seen it. It was being squeezed into a window of intermediate mass, heavy enough to have escaped the earlier machines, but not so heavy as to be out of reach of what could be built. That window was exactly the hardest place to search, because a boson of that mass decays into messy common sprays of particles that are easy to confuse with ordinary collisions. To find it there, you needed enormous numbers of collisions and detectors sharp enough to pick the faint signal out of a roaring background. This was the assignment handed to the machine that would finally do it, the Large Hadron Collider, built in the same 27-kilometer tunnel LEP had vacated. It would collide protons with protons at energies far beyond anything before, producing collisions by the hundreds of millions every second. Somewhere in that torrent, if the theory was right, Higgs bosons would be made, a few among the countless ordinary events, each one flickering into existence and decaying almost instantly. The narrowing was the quiet triumph of the long hunt. Decades of searches that found nothing had done real work, fencing the boson into a corner. By the time the Large Hadron Collider switched on, physicists knew roughly where to aim. The boson, if it was there at all, had almost nowhere left to hide. What remained was to build detectors precise enough to read the sprays, gather collisions in staggering numbers, and watch a particular window of mass for the faint bump that would mean the field had finally been made to ripple. The Large Hadron Collider switched on for serious physics in 2010, and along its great ring sat two enormous detectors, each built and run by a separate team of thousands of physicists from around the world. One was called ATLAS, the other CMS. They were designed differently, using different technologies and different methods, and crucially they worked independently, each blind to the other's results as the data came in. That independence was on purpose. If two separate detectors, run by two separate teams using two separate designs, saw the same thing, it would be very hard to dismiss as a fluke of one machine. Both detectors did the same fundamental job. They sat at points where the proton beams crossed and collided, and they recorded the sprays of particles that flew out of each collision. A Higgs boson, if one was made, would not be seen directly. It would decay almost instantly into lighter particles, and only those decay products would reach the detector. So the teams looked for particular patterns in the debris, combinations the theory predicted a Higgs would leave behind, such as a pair of high-energy photons flying out with a combined energy that pointed back to a parent particle of a definite mass. The trouble was that ordinary collisions with no Higgs involved at all also throw off photons and other particles in similar combinations. The signal was a small excess riding on top of a vast background, a faint bump in a graph where most of the events meant nothing. To see it, the teams had to gather collisions in staggering numbers, hundreds of trillions over the run, and count carefully, watching for a particular mass value where slightly more events appeared than the background alone could explain. Through 2011 and into 2012, both experiments began to see something. At a particular mass, a small excess of events was building up, in more than one kind of decay, in both ATLAS and CMS at once. Neither team told the other what it was finding as the analysis sharpened. They held to their independence right up to the end, each pushing its own data across the threshold that particle physicists demand before claiming a discovery, a level of statistical certainty so strict that a random fluke producing the same bump would be extraordinarily unlikely. The announcement came on the 4th of July 2012 in a packed auditorium at CERN, with the results from both teams presented one after the other. ATLAS showed its bump, CMS showed its bump. They sat at the same mass, found by two independent experiments in multiple decay channels. The room understood at once what it was seeing. A new particle had been found, right in the window the long hunt had fenced off, behaving as the Higgs boson was predicted to behave. Among the audience was Peter Higgs himself, then in his 80s, who was seen to wipe away tears. The particle he had pointed to in 1964, on paper, as a necessary consequence of a field-filling space, had finally been made real in a machine. What made the moment solid, beyond the emotion of it, was that doubled confirmation. One detector finding a bump might be a flaw in that detector. Two detectors, built differently and run separately, finding the same bump at the same mass, was the kind of agreement that does not happen by accident. The field that Brute, Englert, Higgs, and the others had proposed nearly half a century earlier was no longer just the best explanation that fit the evidence. Its telltale ripple had been produced and seen. The discovery answered the central question the mechanism had left open for decades. The field was real. But it also handed physicists a precise new number, the mass of the boson itself, and that number carried its own weight of meaning, both confirming the picture and quietly pointing at problems still unsolved. The new particle's mass came out to about 125 times the mass of a proton in the units physicists use, around 125 billion electron volts. After decades of not knowing where in the range the boson would sit, here at last was the number, measured to good precision by both teams and sharpened in the years since. It landed squarely in the window the earlier searchers had fenced off, heavier than LEP could have made, in the awkward middle region that made it so hard to find. That single value did a great deal of work. The Higgs boson's mass is set by the steepness of the wine bottle wall, the same steepness that fixes how the whole field behaves. So measuring the boson's mass pinned down the last free piece of the mechanism. With it, the standard model became complete in the sense that every particle it predicted had now been found, and every parameter it needed could be measured. The boson was the final missing piece of a structure that had been assembled, prediction by prediction, across half a century. The discovery confirmed the core of the story we have been building. The Higgs field is real, filling space at its fixed strength. Its settling hides the electroweak symmetry, giving the W and Z their large masses while leaving the photon massless, exactly as measured. The fundamental particles get their masses by coupling to this field, each with its own dial. All of that now rested on a found particle, not just a beautiful idea. The mechanism proposed in 1964 had passed its hardest test. The properties of the new particle were checked against prediction, point by point, in the years after 2012. A Higgs boson should have no spin, unlike most other particles, and the measured particle had no spin. It should couple to other particles in proportion to their mass, gripping the heavy ones strongly and the light ones weakly, and the measured couplings followed that pattern. The heavier the particle, the more strongly the Higgs was seen to interact with it, just as the coupling dial picture required. Every test the particle faced it passed as the Higgs boson should. So the title's first half is firmly answered. The Higgs boson is real, and it does its job. It is the visible sign of a field that gives the fundamental particles their mass, and that field is now confirmed beyond reasonable doubt. The W and Z are heavy because of it. The electron has its mass because of it. The top quark grips it hardest of all. For the fundamental particles, the ones with no parts, the Higgs field is the answer to where mass comes from, and the boson found in 2012 is the proof. And yet the value, 125, carried a quieter message that not everyone in that celebrating auditorium dwelt on. A mass that particular, sitting where it does, raises a hard question about why it is not vastly larger, a question we will come to under the name of fine-tuning. The number that completed the standard model also exposed one of its deepest discomforts. The boson was exactly where it needed to be to make the theory work, and being there, it looks strangely, almost suspiciously light. But set that worry aside for now, because there is a much more immediate catch, and it is the one the title is really built on. Everything confirmed in 2012 concerns the fundamental particles and their masses. The celebration was real and earned. The mechanism works. The field is there. Now we have to turn the story over and look at its underside, because for all that the Higgs explains, the mass you actually carry, the weight in your hand, is almost entirely something the Higgs did not give. Here is the turn the whole title rests on. Everything we have confirmed about the Higgs concerns the fundamental particles, the ones with no parts. The electron's mass, the quark masses, the heavy W and Z, all of it comes from coupling to the Higgs field, and all of it is now solidly established. If that were the whole of mass, the story would end in triumph. The Higgs gives mass, the boson proves it, the question is answered. But it is not the whole of mass, it is a small corner of it. Think about what actually makes up the weight of ordinary matter. The stone in your hand is made of atoms. Almost all of an atom's mass sits in its nucleus, in the protons and neutrons packed at the centre, because the electrons around them are nearly 2,000 times lighter and contribute very little to the total. So the mass of ordinary stuff is, to very good approximation, the mass of its protons and neutrons. Weigh the stone, and you are essentially weighing the protons and neutrons inside it. Now the key fact: protons and neutrons are not fundamental particles. They are built things, each one made of smaller pieces, the quarks, bound together by the strong force and its carriers, the gluons. A proton holds 3 quarks in its simplest description, 2 up quarks and 1 down quark, swimming in a furious storm of gluons that bind them. So when we ask where the proton's mass comes from, we're no longer asking about fundamental particles directly. We're asking about a bound system, a little cluster held together by a force. And those quarks inside the proton do get their masses from the Higgs field, just like every other fundamental particle. The up and down quarks have small Higgs-given masses set by their coupling dials turned quite low. So you might expect that the proton's mass is just the sum of its quarks' Higgs masses plus the contribution of the gluons. Add up the parts, as we tried to do at the very beginning with the stone, and you should get the whole. This is exactly the expectation that breaks. When you actually add up the Higgs-given masses of the 3 quarks inside a proton, they account for only a tiny fraction of the proton's total mass, something like 1 part in 100, roughly 1%. The other 99% is not there in the quarks. The proton weighs far, far more than the pieces the Higgs gave mass to. The gluons themselves are massless, contributing nothing through the Higgs at all, so almost the entire weight of the proton, and therefore almost the entire weight of the stone, and of you, has no Higgs mass behind it. This is the quiet catch hidden under the celebrated discovery. The Higgs boson explains the mass of the fundamental particles, and it is right and confirmed. But the fundamental particles' masses make up only about 1% of the mass of ordinary matter. The Higgs is real, it works, and it accounts for a sliver. The other 99% of the weight you carry comes from somewhere the Higgs never touched. So the famous slogan, that the Higgs gives the universe its mass, is true only for a small and special part of mass, the resting mass of the fundamental particles. For the mass that fills the everyday world, the heft of stone and water and bone, the Higgs is almost a bystander. Something else does the heavy lifting, and that something is the strong force, and the strange way energy itself can weigh. To see it, we have to look hard at that missing 99% and where it actually lives. Let us look straight at the gap, because the numbers are startling when you set them side by side. A proton has a certain mass, the standard weight of a single nuclear particle. Inside it sit 2 up quarks and 1 down quark. The up quark's Higgs given mass is tiny, and the down quark's is a little larger but still tiny. Add the 3 together and you get roughly 1% of the proton's mass. 99% is unaccounted for by the quarks themselves. Sit with how strange that is against everything our intuition expects. From childhood we learn that a whole is the sum of its parts. Pour 3 cups of water into a bowl and you have 3 cups of water. Put 3 quarks in a proton and you should have the mass of 3 quarks. Instead you have 100 times that. The proton weighs vastly more than the things it is made of. The parts, added honestly, fall almost completely short of the whole. This is not a measurement error or a fudge. It is one of the most firmly established facts in particle physics, checked many ways. The quark masses are known. The proton mass is known with great precision. The mismatch between them is real and enormous. Whatever supplies the missing 99% is not more particles hiding inside, because we know what is inside 3 quarks and a storm of massless gluons. The mass is there without any massive stuff to carry it. Recall now the door Einstein opened, the one we set aside chapters ago for exactly this moment. Mass and energy are the same currency. Energy that is bound up, trapped, held in place, weighs something. It counts as mass on any scale. So the missing 99% of the proton does not have to come from more matter. It can come from energy, locked inside the proton, counted as mass by the relation between energy and the speed of light squared. The whole can outweigh its parts if the binding holds enough energy, and the proton's interior holds a tremendous amount of energy. The strong force that grips the quarks is the most powerful force in nature, far stronger than electromagnetism or gravity at these scales. The quarks are not sitting quietly. They're flying about near the speed of light, confined to a tiny volume, while gluons stream between them in a roaring, churning field that binds the whole bundle together. All that motion and all that field is energy, vast amounts of it, packed into a space smaller than a trillionth of a centimetre across. That bound energy is the missing mass. The proton is heavy not because its quarks are heavy, but because of the furious energy of the strong force holding those light quarks together. The weight of the proton is, almost entirely, the weight of trapped energy. When you lift the stone and feel its heft, you are feeling, in the deepest sense, not the stuff inside it, but the energy of the force that binds that stuff, dressed up as mass by Einstein's relation. This is the real answer to the puzzle from the first chapter, the gap that opened under the stone. The weight in your hand is mostly bound energy, the energy of the strong force inside every proton and neutron of every atom of the stone. The Higgs gives the quarks their small true masses, the 1%. The strong force, through pure bound energy, gives the other 99. Most of what you weigh is, quite literally, energy wearing the coat of mass. To trust this, we need to understand the strong force itself, why it grips so fiercely, why the quarks can never escape, and how a force can store so much energy in so small a space. That force has its own rich story, with its own discoveries and its own Nobel-winning surprise, and it is where the bulk of your weight is actually made. The strong force is the one that holds the quarks together inside every proton and neutron, and it behaves unlike any force we meet in daily life. The familiar forces weaken with distance. Gravity fades as things move apart, and so does the electric force between charges. Pull two magnets apart and the pull gets weaker the farther you separate them. The strong force does something that sounds backward. As you try to pull two quarks apart, the force between them does not fade. It stays strong and in a sense grows the harder you pull. Picture it less like a spring and more like a band that stiffens as it stretches. When quarks sit close together, oddly, they feel almost free, barely held, able to jostle about as if the force had loosened its grip. But try to separate them, and the force resists more and more, refusing to let them go. You can never pull a single quark out of a proton and hold it alone in your hand. The energy needed to separate it grows without limit, and long before you succeed, something else happens that prevents it entirely. That something is one of the strangest features of the strong force. Pour energy into stretching the bond between two quarks, and at some point there is enough energy in the stretched bond to make brand new particles. The bond, rather than snapping to release a lone quark, converts its stored energy into a fresh pair of quarks that cap off the broken ends. You started trying to isolate one quark, and you ended up with more bound bundles, never a single free quark. This trapping is called confinement, and it is why no one has ever seen a quark on its own. The near freedom of quarks when close together has its own name, asymptotic freedom, and its discovery was a landmark. In 1973, three physicists, David Gross, David Politzer, and Frank Wilczek, worked out the mathematics showing that the strong force weakens at short distances and strengthens at long ones, exactly the reverse of ordinary forces. Gross and Wilczek worked together, with Wilczek then a young graduate student, while Politzer reached the same result independently. Their work explained both the strange freedom up close and the inescapable confinement far off, and it earned the three of them the Nobel Prize in 2004. This behaviour is the engine of the proton's mass. Because the strong force never lets up, the quarks inside a proton are bound with tremendous energy, confined to their tiny volume, never able to escape. The gluons that carry the force are not passive. The strong force is so fierce that the gluons pull on each other as well as on the quarks, building a churning, self-reinforcing field of enormous energy density. All of that energy, the motion of the trapped quarks and the roaring gluon field, is bound inside the proton, and all of it weighs. So confinement and asymptotic freedom together explain where the proton's mass really comes from. The quarks cannot leave. The force binding them holds a vast store of energy, and that energy is the proton's mass, far more than the quark's own Higgs-given masses contribute. The strong force does not need the Higgs to make this mass. It makes mass out of pure bound energy, by the sheer ferocity with which it holds the quarks. The Higgs sets the small intrinsic mass of the quarks. The strong force, through confinement, supplies almost all the rest. This is the part of the mass story that the famous slogan leaves out entirely. The Higgs gets the credit, but the strong force does the heavy lifting for ordinary matter. With both forces now in view, the small Higgs contribution and the large strong force one, we can finally balance the books and say cleanly what each one gives and why both are needed for you to have any weight at all. Let us settle the balance plainly, because the two sources of mass work together in a way that is easy to state once both are in view. The Higgs field gives the fundamental particles their intrinsic masses. The strong force, through the bound energy of confinement, gives protons and neutrons almost all of their mass. The first is a small contribution to ordinary matter, around 1%. The second is the overwhelming bulk, around 99%. Both are real, both are needed. Neither alone tells the whole story of the weight in your hand, but the two are not simply side by side, independent and unrelated. There is a quiet dependence between them that is worth seeing, because it rescues the Higgs from looking like a bystander even for ordinary matter. The small Higgs masses of the up and down quarks, the 1%, are what make atoms the way they are. The down quark is slightly heavier than the up quark, and that small Higgs-given difference is part of what decides whether a given nuclear particle is a proton or a neutron, and which way certain nuclei decay. The Higgs contribution is small in weight but large in consequence. Imagine, as a thought experiment, turning off the Higgs field entirely. The strong force would still bind quarks into protons and neutrons, and those bound bundles would still have most of their mass, because that mass comes from strong force energy, not from the Higgs. So ordinary matter would still be heavy. But the quarks would lose their small intrinsic masses, the electron would become massless and fly off at the speed of light, unable to settle into atoms, and the delicate balance that lets nuclei and chemistry exist would collapse. The world would still have mass, but it would have no atoms, no chemistry, no us. So the honest picture is a partnership with two very different jobs. The strong force provides the spark of heft, the great bulk of the weight, by binding quarks with enormous energy. The Higgs provides the fine settings, the small intrinsic masses that make the difference between one particle and another, and let stable matter form at all. The bulk of your weight is strong force energy. The structure that makes you more than a heavy blur is the Higgs. Take away either one and the world you know does not exist. This is why the title's question is sharp rather than dismissive. The Higgs did not fail. It solved exactly the problem it was built to solve, the mass of the fundamental particles, and solved it so well that the boson's discovery completed the Standard Model. It simply does not solve the problem most people think it solves, the weight of everyday things, because that problem belongs mostly to a different force. The mass problem was never one problem, it was two, layered together, and the Higgs answered the smaller, deeper layer. Saying this clearly dissolves a great deal of confusion. When you hear that the Higgs gives the universe its mass, you can now hold the truer version. The Higgs gives the fundamental particles their mass, which is a small fraction of ordinary matter's weight, while being essential to the world's structure. The strong force gives the great bulk of ordinary matter's weight through bound energy, with no help from the Higgs at all. Both are confirmed, both are understood. The slogan was just pointing at the smaller of the two. And yet, even within the part the Higgs does explain, there is a deeper dissatisfaction waiting. The mechanism tells us how the fundamental particles get mass, but not why their masses take the particular values they do. It gives the machine without setting the dials. That gap, the difference between explaining the mechanism and explaining the numbers, is the next layer of the mass problem, and it is one the Higgs leaves wide open. Return to the coupling dials, the per-particle settings that fix how strongly each fundamental particle grips the Higgs field. The mechanism says a particle's mass is its dial, times the field's fixed strength. That is a real explanation of how mass arises, but it quietly hides a failure that becomes obvious the moment you ask a simple question. Why is each dial set where it is? Why does the electron's dial sit at one tiny value, and the top quarks at a value hundreds of thousands of times larger? The honest answer is that the Standard Model does not say. The dials are not predicted by the theory. They are measured in experiments and then put into the theory by hand as inputs. The model is like a beautiful machine with a row of knobs on the back, and physics has carefully measured where each knob is turned, but nothing in the theory explains why they sit there. The Higgs mechanism gives the form of the answer, mass equals coupling times field strength, while leaving every actual coupling as a brute fact handed to us by measurement. This matters because it means the Higgs does not really explain the masses of the fundamental particles in the deepest sense. It explains how they can have mass at all, which was a genuine puzzle, the one the symmetry forbade. It does not explain why the electron weighs what it weighs, or why the muon is about 200 times heavier than the electron, though it seems in every other way to be the same kind of particle. These numbers are not derived, they are read off the world and accepted. Count them up and the scale of the gap becomes clear. The standard model has around 20 numbers that must be measured and fed in, and a large share of them are these mass-related couplings, one for each massive fundamental particle. That is a lot of free settings for a theory often praised as our deepest. A truly complete theory might explain those numbers, deriving them from some smaller, simpler principle. The standard model does not. It organises the particles and forces beautifully, then asks us to supply the masses from outside. There is a way physicists describe the discomfort. A good theory should explain more than you put into it. You would like to feed in a few deep principles and have the rich variety of the world come out. With the fundamental masses, it is the reverse. You feed in the whole list of masses, one by one, and the theory uses them but never accounts for them. The pattern of the masses, their strange spread across many factors of 10, sits there as raw data, unexplained, almost taunting in its lack of any obvious rule. So even in the domain where the Higgs is the hero, the resting mass of fundamental particles, it answers only half the question. It tells us the mechanism by which those particles acquire mass. It does not tell us why the masses come out as the specific numbers we measure. The slogan that the Higgs explains particle masses is true for the how, and false for the why. The why remains one of the open problems of physics, untouched by the discovery in 2012. This is not a small footnote. The unexplained spread of the fundamental masses is one of the loudest hints that the standard model, for all its success, is not the final word. A deeper theory underneath it might one day derive these numbers from something simpler. The way the strange list of chemical elements turned out to follow from the simple structure of the atom. Until then, the masses stand as a row of measured facts with no reason behind them. To feel the full weight of that mystery, it helps to look at its two most extreme faces, the heaviest fundamental particle and one of the lightest, sitting side by side with no explanation for the vast distance between them. Set the top quark and the electron next to each other, and the mystery of the masses stops being abstract. Both are fundamental particles, each a point with no parts inside, each getting its mass the same way, by coupling to the same Higgs field. In that deep sense, they are the same kind of thing, particles that grip the field and gain mass from it. Yet the top quark is about 340,000 times heavier than the electron. The same mechanism, the same field, and a spread of that size between two members of the cast. The top quark is the heavyweight champion of the fundamental particles. It is so heavy that a single one weighs about as much as an entire atom of gold, which holds dozens of protons and neutrons. Think about that. 1 point particle, with no size and no parts, outweighs a whole atom built from scores of bound nuclear particles. Its coupling dial is turned nearly to the maximum the theory allows, gripping the Higgs field harder than anything else we know. It is so heavy that it decays almost the instant it forms, never living long enough to bind into anything. The electron sits at nearly the opposite end among the everyday particles. It is light enough to be flung about easily, light enough that it forms the soft, far-reaching clouds around atomic nuclei that make all of chemistry possible. Its coupling dial is turned far down, barely engaging the Higgs field, and between the top's near maximum grip and the electron's faint one lies a span of hundreds of thousands, with the other particles scattered across it, the muon here, the various quarks there, no two quite alike. Now the sharp question, why this spread? Both particles swim in the same field. Nothing about the Higgs mechanism says the dial should differ at all, let alone by such an enormous factor. If you knew only the mechanism and not the measurements, you would have no way to guess that one particle would grip the field 300,000 times harder than another. The theory permits any setting and predicts none. The vast distance between the top quark and the electron is measured, recorded, and entirely unexplained. Physicists sometimes call this the flavor puzzle, the question of why the different kinds, or flavors, of fundamental particle have the masses they do, arranged in the strange pattern we find. The masses do not seem random exactly. They fall into rough family groupings, 3 generations of progressively heavier particles, as if there were some hidden order. But no one has found the rule that sets the actual values. The pattern hints at structure underneath, a deeper layer that would explain the dials, but that layer has not been found. This is the unexplained spread laid bare. The Higgs gives every one of these particles its mass, faithfully, by the same mechanism. It does not say why the top quark's mass dwarfs the electrons, or why the values land where they do rather than anywhere else. The contrast between the heaviest and the lightest is the mystery in its starkest form. 2 particles of the same fundamental nature, born of the same field, separated by a gulf no theory yet explains. And the electron and top quark, for all their difference, are at least particles whose masses fit the standard picture cleanly. There is another set of particles whose masses strain the simple Higgs story almost to breaking. Particles so light and so strange that for a long time they were thought to have no mass at all. They are the faintest things in the cast, and their tiny weights point past the standard model toward physics we do not yet have. The neutrinos are the ghosts of the particle world. They are leptons, cousins of the electron, but they carry no electric charge and almost never interact with anything. Trillions of them are streaming through your body every second, born in the heart of the sun, and nearly everyone passes straight through the Earth without touching a single atom. They are so faint, so reluctant to interact, that detecting even a few of them takes enormous tanks of material buried deep underground, watched for the rarest of collisions. For decades, neutrinos were assumed to be exactly massless, like the photon. They were so light that no experiment could find any mass at all, and the original standard model was written with massless neutrinos built in. They seem to fit the role of weightless particles, flying at or near the speed of light, never settling, never resting. If they had no mass, they needed no Higgs coupling, and the question of their mass did not arise. That tidy picture held for a long time, then experiments overturned it. Starting in the late 1990s, detectors studying neutrinos from the sun and from cosmic rays striking the atmosphere found that neutrinos change their type as they travel, one kind shifting into another along the way. This shifting, called neutrino oscillation, can only happen if neutrinos have mass, even a tiny amount. The discovery, recognized with the Nobel Prize in 2015, proved that neutrinos are not massless after all. They weigh something, just an extraordinarily small something, and that smallness is the problem. Neutrino masses are not just light. They are at least 1 million times smaller than the electron's mass, which is itself one of the lightest. If a neutrino got its mass the ordinary way, by coupling to the Higgs field like every other particle, its coupling dial would have to be turned almost unimaginably close to 0, far lower than any other particle, with no explanation for why it sits there. The straightforward Higgs story can be made to give neutrinos mass, but only by setting a dial to a value so tiny it looks absurd, an extreme fine-tuning that cries out for a reason. Many physicists suspect the neutrinos get their mass a different way, not purely from the Higgs at all. There is a proposed mechanism, often called the seesaw, in which the lightness of the known neutrinos is tied to the existence of much heavier, undiscovered partner particles. The 2 masses balance like the 2 ends of a seesaw, one pushed down as the other rises. If that idea is right, neutrino mass would be a sign of new physics beyond the standard model, a heavier scale of particles we have not yet reached. But the seesaw is unconfirmed. No one has found the heavy partners, and the true origin of neutrino mass remains open. So the neutrinos sit as a quiet rebuke to the simple Higgs picture. They have mass, which the original theory denied. Their masses are so small that the ordinary Higgs mechanism explains them only by an uncomfortable stretch. And their best alternative explanation reaches beyond the standard model into territory we have not confirmed. The lightest particles in the cast may carry the loudest clue that the Higgs story, complete as it looks, is not the end of the account of mass. The neutrinos point outward, past the edge of the known, toward physics still to be found. But there is also a problem pointing inward, at the Higgs boson itself, at the very number measured in 2012. That number, 125, should not be as small as it is, and the reason it is small is one of the deepest discomforts in all of physics. The boson's measured mass, around 125, completed the standard model. It also opened a wound that physicists had worried about for years before the discovery, and the measurement only sharpened it. The trouble is that according to the theory's own machinery, the Higgs boson should be enormously heavier than it is. Not a little heavier, heavier by a staggering factor many trillions of times over. The fact that it is light instead is one of the strangest puzzles in physics, and it has a name, the hierarchy problem. To feel the problem, you need one idea from quantum physics. In the quantum world, no particle is ever truly alone. Empty space around any particle churns with fleeting temporary particles that flicker in and out of existence, too briefly to be caught, but real enough to affect the particle they surround. Every particle's measured mass includes contributions from this churning cloud of fleeting partners. For most particles, those contributions are modest and well-behaved, nudging the mass a little. For the Higgs boson, the contributions are not modest. Because the Higgs couples to mass, and couples most strongly to the heaviest things, its churning cloud is dominated by the heaviest particles, and the corrections to its mass from that cloud are huge. When physicists calculate how much these quantum contributions should add to the Higgs mass, the answer comes out vastly larger than the measured value, pulled up toward the highest energy scales in nature, perhaps the scale where gravity itself becomes strong. Left to the natural workings of the theory, the Higgs should be heavy beyond imagining. Yet, it is light. The measured 125 is tiny compared to what those quantum corrections seem to demand. For the small measured value to emerge, the enormous contributions must very nearly cancel, leaving only a tiny remainder. And the cancellation has to be almost perfect, with the huge positive and negative pieces matching to dozens of decimal places to leave behind the small number we see. Nothing in the theory requires that cancellation. It just has to happen, exactly, by what looks like an absurd coincidence. This is the fine-tuning worry. A theory that needs a coincidence accurate to dozens of decimal places with no reason behind it feels deeply unsatisfying, like a pencil found balanced on its tip with no one to have balanced it. Physicists strongly suspect that such a precise cancellation is not a coincidence at all, but a sign of something missing, some deeper structure that makes the lightness of the Higgs natural rather than miraculous. The smallness of the boson's mass is read as a clue that the standard model is incomplete. For decades, the most popular proposed fix was an idea called supersymmetry, which pairs every known particle with a heavier partner. The partner's quantum contributions would have the opposite sign, cancelling the dangerous corrections automatically, no fine-tuning required, and keeping the Higgs naturally light. It was an elegant solution, and many expected the Large Hadron Collider to find these partner particles alongside the Higgs. So far, it has not. The searches have come up empty, and the simplest versions of supersymmetry are now in serious trouble, though variants survive. So the very number that crowned the Higgs discovery carries an unsolved problem at its centre. The boson is light, far lighter than the theory naturally allows, and no confirmed explanation says why. The hierarchy problem remains open, its favourite solution unfound, a sign that something about mass and the Higgs is still not understood at the deepest level, and this is a problem within the matter we know. There is a far larger gap waiting in the dark, in the mass that fills the universe but is made of nothing in our cast at all. Step back from the particles and look at the universe as a whole, and the mass problem grows far larger than anything inside a proton. When astronomers weigh galaxies by watching how fast their stars orbit, they find the galaxies are far heavier than the visible matter in them can account for. Stars, gas, dust, everything that shines or can be seen adds up to only a small fraction of the mass needed to hold a galaxy together and explain its motion. There is vastly more mass present than there is visible stuff to carry it. This unseen mass is called dark matter, and the evidence for it has piled up for decades from many independent directions. Galaxies spin too fast for their visible mass to hold them. Clusters of galaxies bend, passing light more sharply than their glowing matter should. The pattern of the oldest light in the universe, the faint afterglow of the early cosmos, carries the fingerprint of this extra mass shaping how everything formed. Tally it all, and the conclusion is hard to escape. Most of the matter in the universe is invisible, and it outweighs the ordinary kind by roughly 5 to 1. Here is the part that matters for our story. That dark matter is not made of any particle in the standard model. It is not protons and neutrons, not electrons, not anything whose mass the Higgs gives or the strong force builds. Whatever it is, it does not shine, does not interact with light, and slips through ordinary matter almost as freely as the neutrinos do, though it is far more plentiful. The entire account of mass we have built, the Higgs for fundamental particles, the strong force for ordinary matter, says nothing about where the dark matter's mass comes from, because dark matter lies entirely outside the cast. So the mass problem has a cosmic layer that dwarfs the others. We have explained, between the Higgs and the strong force, the mass of ordinary matter, the stuff of stars and planets and people. But ordinary matter is only about 1 part in 6 of all the matter in the universe. The other 5 parts are dark, unknown, their mass real and measured by its gravity, their nature a complete mystery. The Higgs story, even joined with the strong force, accounts for the mass of only the small visible slice. There have been many guesses about what dark matter is. The leading idea for years was a new kind of heavy particle, not in the standard model, that interacts only weakly with ordinary stuff, which would also have made it a natural partner to some solutions of the hierarchy problem. Experiments built deep underground have hunted for these particles for decades, watching for the rare, faint nudge of a dark matter particle striking an ordinary nucleus. So far, like the search for supersymmetry, these hunts have come up empty. The particle, if it exists, has not shown itself. If dark matter is a particle, then it too must get its mass somehow, and we do not know whether the Higgs has anything to do with it. Perhaps it couples to the Higgs field like ordinary particles do, or perhaps its mass comes from some entirely different mechanism in a hidden sector of physics we have not yet touched. We cannot say, because we have not identified the particle, if it is a particle at all. The origin of most of the matter mass in the universe is simply unknown, so the sky itself holds the largest unsolved piece of the mass problem. The Higgs gives mass to the fundamental particles of ordinary matter. The strong force builds the bulk of ordinary matter's weight, and all of that, the entire story we can tell, covers only the visible 1/6 of the universe's matter. The rest is dark, massive, and unexplained. The mass problem, far from being solved, opens outward into the cosmos, where most of it remains untouched. Let us gather the open questions, because seeing them together shows just how much of the mass problem still stands. The Higgs boson was found, real and confirmed, and it gives the fundamental particles their mass through a mechanism we now understand. That is a genuine triumph, one of the great achievements of physics. But around that solved core lie several unsolved problems layered from the small scale of particles out to the vast scale of the cosmos, and not one of them is closed. First, the values of the fundamental masses. The Higgs explains how particles get mass, but not why their masses take the specific values they do. The coupling dials are measured, not derived, and their strange spread from the faint electron to the gold-heavy top quark follows no known rule. A deeper theory might one day explain the pattern, but none has. The flavor puzzle, the question of why the masses are arranged as they are, remains wide open. Second, the neutrino masses. They are real, proven by oscillation, but so tiny that the ordinary Higgs mechanism explains them only by an uncomfortable stretch. The favoured alternative, the seesaw with heavy hidden partners, would point beyond the standard model, but its partners have not been found. How neutrinos get their mass is genuinely unsettled, and the answer may require new physics. Third, the hierarchy problem. The Higgs boson is far lighter than the theory naturally allows, kept light only by a cancellation so precise it looks like a miracle. The leading fix, supersymmetry, predicted partner particles the Large Hadron Collider has not found, at least not in its simplest forms. Why the Higgs's light remains one of the deepest discomforts in physics, its resolution unknown. Fourth, dark matter. Most of the matter in the universe is invisible, its mass measured by gravity, its nature unidentified. It is made of nothing in the Standard Model, and whether the Higgs plays any role in its mass is unknown, because we have not found the particle, if it is one. The largest share of matter mass in the cosmos lies entirely outside the account we can give. These four are not isolated. Several of them point hopefully toward the same kinds of new physics. A heavier scale of particles could explain the neutrino masses through the seesaw, tame the hierarchy problem, and supply a dark matter particle all at once. That convergence is part of why physicists keep searching for new particles beyond the known cast, building larger machines and more sensitive detectors. The hope is that one discovery might unlock several of the open doors together. So far, the new particles have not appeared, and the proposed fixes remain unconfirmed. It is worth saying plainly, in the calm spirit of honest physics, that none of this diminishes what was achieved. The Higgs mechanism is correct as far as it goes. The boson is real. The mass of the fundamental particles is understood in its mechanism, and the mass of ordinary matter is understood through the strong force. What remains open is not a refutation of any of that. It is the next layer, the deeper why behind the confirmed how, and the wider universe beyond the matter we know. The title asked why the Higgs boson still has not solved the mass problem. The answer, gathered here, is that it solved one real and important piece, the mechanism of fundamental mass, and that the mass problem was always far larger than that one piece. It reaches down to unexplained numbers, out to ghostly neutrinos, inward to the boson's own suspicious lightness, and outward to the dark mass of the sky. The Higgs lit one room in a very large house. With all of this in view, we can return, at last, to the stone in your hand and say in the simplest words what gives it weight. Pick up the stone again, the one you were holding at the very beginning, and feel its weight settle into your palm. We can now say, in plain words, where that weight comes from, and the answer is richer than the one we started with. The simple picture was that the stone is heavy because it is made of stuff, and the more stuff, the more weight. That picture is not wrong, but it was hiding almost everything interesting underneath it. The stone is atoms, and the weight of the atoms is almost all in their nuclei, in the protons and neutrons packed at the centre. Those protons and neutrons are made of quarks, and the quarks are bound by the strong force. When you weigh the stone, about 1% of what you feel is the intrinsic mass of those quarks, the mass the Higgs field gives them by their coupling to it. The other 99% is the bound energy of the strong force holding the quarks together, energy counted as mass by Einstein's relation. The weight in your hand is mostly trapped energy, dressed as mass, made by the fiercest force in nature. So the Higgs boson, real and confirmed, found at last in 2012, did not give the stone its weight. It gave the fundamental particles their masses, which is a small fraction of the stone, and an essential one, because without it there would be no atoms and no chemistry and no stone at all. But the heft itself, the press against your palm, is the strong force at work inside every proton and neutron, a thing the Higgs never touched. That is why the Higgs has not solved the mass problem. It solved a deep and narrow piece of it, and the weight you actually feel belongs mostly to another force entirely. And even that is only the part we understand. Why the fundamental masses take their particular values, no one knows. Why the neutrinos are so impossibly light, no one is sure. Why the Higgs boson itself is so much lighter than it should be, no one can yet explain. And why most of the matter in the universe is dark, unseen, made of nothing in our cast, remains one of the largest open questions in all of science. The mass problem was never a single locked door. It is a long hallway of them, and the Higgs opened one. There is something steadying in seeing it this way. The universe did not hand us its weight in a single simple fact. It built that weight in layers, a small contribution from a field that fills all of space, a vast contribution from a force that binds the smallest things, and beyond the matter we know, a dark abundance we have only begun to weigh. Each layer was hard-won, measured by careful people over long years, and each one opened onto a deeper question. That is not a failure of physics. It is how understanding actually grows, one honest room at a time. So the next time you lift something and feel its weight, you can hold the truer story along with it. Most of that weight is energy, bound inside particles too small to see, by a force you will never feel directly, but which is doing furious work in every atom of you, and everything around you. A sliver of it comes from a field humming in the empty vacuum, a field whose ripple we finally caught after half a century of looking. And the universe holds far more mass still, out in the dark, waiting for someone to understand it. The weight in your hand is real, and most of where it comes from is now known, and some of it is still a mystery. That is the honest shape of the answer, and it is enough to make an ordinary stone feel like a small piece of the whole universe, which is exactly what it is.